get going to the rest of their day.
Sure. Thank you very much, Tricia. And first of all, good morning, everybody. Wow, we're really excited to have this opportunity this morning to share with you some of the research that we're doing here in University College Cork. First of all, very big thanks to Tricia and all the gang at Energy Exemplar for giving this opportunity. My name is Paul Deane. I'm a researcher here in the university. I'm here with my colleague Fiac Gaffney. Fiac actually leads a lot of our research in European electricity power systems. Of course, one of the nice things about working in a university like this is that we get lots of fun things to think about the future. We think about the future of electricity, the future of transport, and the future of heating. And actually, to help that thinking process, PLEXOS is one of the main tools that we use to understand what the future might look like. So very briefly this morning, it's a beautiful sunny day here in Cork, which is quite unusual. We're going to share with you some of that thinking that we've been doing. We're actually going to look at some pretty extreme and pretty radical versions of what the future European power system may or may not look like. The reason why we chose these extreme systems is really just so you can understand as PLEXOS users how to get the most out of the software and how to get the most out of PLEXOS. So we're going to be looking at some visions of really ultra high levels of renewable energy within the European power system, and then all the problems that that stuff brings along and all the challenges such as inertia, rock off, high temporal resolution, storage and flexibility. And we'll touch on a number of these issues through the presentation. Now, before we kick off, we're not saying that we know how best to do all these things. There's lots of things that we have done wrong, and really this is kind of an evolving learning process that we are going through here. But we're very excited to share with you some of our experiences, and we'd be very happy and delighted to hear from you, the PLEXOS community and the wider PLEXOS audience, about how things could be done better and maybe some of the future challenges that you are thinking about as well. So I'm going to hand you over to my colleague Fiac. Fiac is going to be the pilot for this presentation. I'm going to be the co-pilot. We're probably going to be, it's about 30-35 minutes, and hopefully we'll have about 15-20 minutes for questions at the end. So as we're tipping through the presentation, maybe note down some questions, maybe punch them into the Q&A, and Trish can maybe bundle them together for us, and we'll do our very best to answer and share with you at the very end. So Fiac, it's all yours.
Thank you. So our presentation then is going to be about the stuff that we're learning all the time when using PLEXOS, and it's mainly focused around Europe, but the techniques that we're going to talk about should be transferable as far as we can see. All right. So the topics then we're going to touch upon, the three of them are here, but really it comes down to new challenges and then the new opportunities that bigger computing brings, and that's what we're going to talk about. Again, this is the first section, so here we are going to focus on Europe, but we hope that everybody can learn some of the techniques that we use and try and use them in your own areas, in your own countries, whatever you're modeling. So there's new challenges ahead. We can see that it's everywhere. We can see that there's this decarbonization ambition in a lot of countries in the world, and in the power sector, the focus is changing from just traditional generation to variable generation, and that flexibility that the system must bring, and that nexus in between. And it's challenging for us. And I suppose moving forward, then our focus has to go beyond the power sector. The power sector is the equivalent of around 20% of all energy used. So we need to go wider into the other sectors. To do this, storage is obviously very important, and seasonal storage is really a new challenge for us. And then flexibility in around the demand, and then different types of generation that we're going to talk about, and we have to be ready for when they come online. And all these things then are brought together then when we look at system operation and how, I suppose, when you have a lot of variable generation, we have to be able to look at the frequency stability of power system, and then equally important is the portfolio adequacy, and we will touch upon these things as we go through the presentation. Just the next couple of slides, I'm just trying to lay kind of a scenario out that we are modeling at the moment, and it's looking at, I suppose, an extremely ambitious scenario. Sorry, can I? Yeah. So it's a 100% decarbonized energy system for the European region that we're going to look at. And if we just compare to 2017 installed generation capacities, we can see here that there is a significant increase in variable generation. And here, just to put to draw your focus here, that's the equivalent to 82% of the portfolio is variable renewable energy. This obviously is creating a new need for the robust results and just for understanding the challenges ahead from an operational point of view alone. When we look at storage then, we compare 2017 numbers, which really we have little or no storage other than pumped hydro. And here I'd like to point out that the STES is short-term energy storage, and the UTS is underground thermal energy storage. So both of these are thermal, and but we'll come back to that because they play a large part, especially the underground thermal energy storage. So we can compare then to the 2017 and this high variable renewable scenario. We can see that a very high percentage of storage is thermal. And that brings its own problems, because if we can't store energy and then convert it back to electricity, we have a big problem. And that's, I suppose, what we are seeing here is that void in technologies that can bring energy back into power. We can assume that power to gas produces hydrogen, which can be converted back. But in this scenario, it's a published scenario that we are aligning with. So, and they assume that power to gas, the hydrogen from that, is only used for transportation. Next, we'll talk about demand. And when we think about demand, we look at like the 2016 numbers here. We see basically all our demand is inflexible. It's inelastic. There's very, very little that can move in the way that tomorrow's demand might need to. And this scenario is for 2050, but what we're laying out here is we're trying to show the difference in estimated demand and what type of demand it is. So there's 25% inflexible, and then that 75% flexible demand is made up of demand response, power to gas or power to X, heat loads and cooling loads. So when we model this scenario, what we're looking at the entire energy system. The transportation sector is accounted for in the power sector because of electrification of vehicles, and the remainder is based on hydrogen. So what we are doing then is we have to look at this thermal aspect and try include the thermal sector and model that as well as the power sector. And that's what I'm going to show you now, how we actually do this. Inside a region, here we see the French region, and we have two nodes, a power and a heat node. Inside the nodes then, we can see the power node is set up exactly like any power system generally would be. You have generators, you have purchasers, which are demands, you have batteries, interconnectors. It's very standard. Inside the thermal node then, what we have is we have thermal generators. So we have geothermal heat, we have solar thermal, and then we have the underground thermal energy storage. We have purchasers, we have batteries, and here, well, we say batteries, but really this is storage, and we use that for short-term energy storage. And excuse me, in the latest versions of PLEXOS, you can actually change the classes names, which is fantastic, because it's actually a way of documenting your model without having to go and just, I suppose, write up a full document. It's just, it will help make it understandable to someone maybe that's not used to the model.
Yeah, this is probably, just jumping in there, Fiac, you folks are probably looking at some of those capacities and going, wow, they look really crazy, they look really extreme, and they are, and they are like that on purpose for a couple of reasons. One, this is looking at a fully decarbonized energy system, and I think what's really exciting about using PLEXOS in this way is that you can jump beyond your comfort zone of just the electrical power system, which is, as Fiac said, it's 20% of the energy we consume, and look at the other 80% of the problem. Interestingly enough, as Fiac mentioned there, actually, when we started this research maybe a year or two ago, there wasn't a dedicated heat node within PLEXOS, but the newest version of PLEXOS now has a dedicated heat node. So as PLEXOS users, we'd encourage you all to maybe explore some of these things, because it does open up a lot of really exciting avenues for exploring what the future power system, but more importantly, what the future energy system could look like.
And then just to tie off this representation of the thermal sector, there's one missing link, and that is the link between nodes. And that's what we're talking about here. We're going to show the intersectoral unilateral flow of energy. So electricity, if there's excess electricity, rather than curtail that energy, it is stored as thermal energy in seasonal storages that are outlined by the source material. And how that transformation happens is through dielectric heaters, high efficiency heat pumps, these sort of technologies that are already on the market. So what we're seeing here is that if there is excess electricity, it can be stored as thermal, but it cannot be reversed. And that's the key point that we're trying to get across. So that's a very, it's an important assumption.
Yeah, and this is one of the fun things you can do with PLEXOS, with the ability to have your own constraints. And I guess one of the lessons we learned pretty early on is, if you're going to put in constraints like this, it's really fundamentally important to have a look at the LP equations. Look at the linear programming equations through the inactive diagnostic. And there's a really cool feature that Energy Exemplar posted up on their website, where they have a syntax reader. You can incorporate that into your text editor, and that really makes life reading the LP files a lot easier, because sometimes those constraints can be quite tricky. They might not be doing what you think they're doing. So if you are setting up new constraints with different technologies, new technologies, it's really worthwhile to have a look at the fundamental equations driving those before they get to the optimizer using the LP viewer.
And it's often better using a small model, isn't it? Like
The
smaller the model, the easier, the more transparent things are. And that's what we try and do with pretty much every new technique that we use, because otherwise you just get lost in the data. So in terms of flexible demand, then this is a model in a different way. What we do here is, it's a unique approach, but I'll talk you through it in a moment. So hydrogen here, the assumptions are that hydrogen is created from power to gas for transportation purposes only, and not demand response. And one of the key things here I want to get across is that demand must be met using previously stored hydrogen, or hydrogen converted at the time of demand. And that may seem obvious, but it is very important to remember that when you're setting up flexible demand in the way we do, which may not be the correct way, but this is the way we do it. So at the moment, but the way our approach is that flexible demand is modeled in two individual parts. Firstly, you have the demand, which is a static, it's in the purchaser class, just the way any demand may be. And in this assumption, or in this scenario, it's a constant load. We assume that hydrogen is needed and all across the year at the same demand. However, you can input a CSV file here with a profile. That it doesn't really matter to us. It's more about we're just aligning with the approach that we are trying to replicate. Flexibility then is the next thing, and flexibility is modeled in the same way as pumped hydro is, where you have an upper and lower storage connected with a turbine in between. And this is the way battery technology used to be represented in PLEXOS until the battery class was created. So here we see, we can see the max capacity is 102 gigawatt hours, and that is aligning with it, with your assumptions. However, what I would draw your attention to is the initial volume is 0. So the upper storage, which we're looking at, the upper storage is empty at the start of the simulation, and then that has to fill up before it can be used. We can see here that the lower storage is full, so it's ready to pump up. And this is just something that we wanted to mention before we move on?
Yeah, I guess maybe just jumping in there, Fiac, that's something that we'd probably like to see maybe in future versions of PLEXOS, this power to X class. As Fiac said, you know, before a lot of us were modeling things like batteries using dummy pump storage technologies, and that's fine, but often what you will see is that when PLEXOS incorporate those things as a fixed class, it just makes the whole thing a little bit more elegant, a bit more tidy, and a little less clumsy. So maybe power to X is one of those things. Certainly not within the investment cycle, but it's probably coming through in the next maybe 10, 12 years, probably in Europe. So that's something maybe that we could think about as a community as well, I guess. Yeah.
And to finally, just to tie off the link, to show you the link between the demand and the flexibility when you're replicating this, is the fixed load for the turbine that's associated with that storage. That has the same fixed load as the demand. So what we're saying here is that demand is 2.138 gigawatts constant, and the output of that turbine, which has flexibility incorporated because it has an upper storage and lower storage, has the same output. So that's the link, that the missing link, if you were maybe struggling to find out how they work together. So next then, we're going to look at, from an operational perspective, we're going to look at, like, when you have a system that is 82% variable renewable energy, the questions are, where's the inertia coming from? How can you control such a system that has very little synchronous energy? And that's what we're going to look at here. This is going to be, we're going to focus on the Central European continental synchronous area. So what we see here is, this is the scenario we've talked about from the start. So it's the high variable renewable energy scenario. And we can see from an operational perspective that we're possibly heading into unknown territory. Well, certainly unknown territory as in today's standards. What we then do is add some dispatchable power. Approximately 8% of installed capacity is replaced with dispatchable capacity. And we do not talk really about what type of dispatchable power, because it's all about the effects of it, whether it's nuclear, CCS, coal, whatever. So next, here's the effects on inertia from just having 8% for the European grid. So really what we're seeing here is that we're really pushing back into the area that we know we can handle. And the thing is, this is all very easily done in PLEXOS. And if we wanted to move a step further, we can also replicate the effects of having that dispatchable power, and if it can act as a synchronous condenser, which maybe future dispatchable capacity can do that. And you can do that in PLEXOS very easily. Unfortunately, I didn't have time to model that, but it's very easy to do, and you can see then when a generator is out of merit, it can act as a synchronous condenser and provide inertia. While it's not the exact same inertia or level of inertia as when it's generating, it's a third or a quarter of the inertia, and it adds something. It's making full use of the capacity, which is very important.
I guess what's nice about this technique here is that while PLEXOS isn't a dynamic electricity modeling package in terms of some of this sub-grid stuff, looking at these issues like inertia or walk-off are very useful in PLEXOS, because it's about raising flags. So if you're dipping into that red zone, that means really, okay, I need to start worrying about this issue in a lot more detail. So certainly I think the work that Fiac has done here is very insightful, actually, for understanding where the power system can comfortably operate and where that becomes a little bit more tricky and challenging.
Yeah. So next then we're going to go and we're going to look at ancillary services, because again, going back to our scenario where there's 82% of installed capacity is variable renewables, the questions then are who's providing reserve and how, really. So to lay a little bit of I suppose just a little bit of background then, we are looking at a combination reserve which combines secondary, tertiary and replacement reserves. And we are focusing on upward regulation because it's the more challenging, because I suppose for downward regulation, you can possibly curtail and just dispatch down plants. So there's two things I want to talk about. So the first thing is that we assume a static reserve of 3 gigawatts, which for mainland Europe. And then also, this is kind of something unique that what we're doing is we're setting a dynamic reserve, which is a percentage of generating variable renewable energy. And this is, this methodology has been, it's from published data, and we use it, and we use I suppose, a very unique way of setting this reserve, which we'll talk about in the next slide. But in this slide, we just want to point out who is providing the reserve, what are the issues, and then what are the effects if we tweak that with a little bit of dispatchable power. So here, first of all, we're looking at the high VRE scenario, and I've grouped together 3 generation types that I call traditional reserve providers. And it's not very accurate because while pumped hydro is our traditional, we know how that works. Concentrated solar power the technology we understand, we understand that that's why it's grouped there, because the alternative 66% comes from deloading variable renewable generation. And just to identify what that exactly is if you have a wind farm that can produce 100 gigawatts, or is forecast to generate 100 gigawatts in hour 1 in any day, that could be deloaded back to say 90% of that, with that 10% there for upregulation, for injecting power into the system. And that's kind of unknown territory. There's definitely going to be, there's a lot of pros and cons to that, but it's just unknown territory really is what we're saying, and we're trying to flag these issues with such an approach. So what we do then is we suggest a level of dispatchable generation and as we did in the last slide. So here we say, so if there was that 8% of dispatchable power, it provides nearly 20% of the reserve requirements, but there's a knock-on effect that because this power is generating, it's displacing some of the hydro and pumped hydro and solar CSP generation, and then that can be kept for reserve. And as we see here, instead of it being 34% of reserve coming from traditional sources, it's now 85%. So the risk around here is much lower in terms of the unknown strategies of how to deload variable renewable energy.
What I like actually about the way Fiac has set this up is that because it's an integrated overview on the full energy system, there's also things like power to gas in there. So in Europe at the moment, we hear a lot of business cases about maybe curtailed renewable energy being sent for free to provide power to gas. But this decision support tool that Fiac has set up here also allows us to understand if you are a wind farm operator, well, if you deload your generation, rather than send your electricity to free for power to gas, maybe there's a bit more financial gain from actually deloading that and holding it as a reserve capacity as well. So I think that's a nice and new insight coming from this analysis.
And it's new questions that need to be, yeah. Now, how we actually implement this in the software is in PLEXOS so we're looking at using variable renewable energy to set the reserve contingency. So here, first of all, we use a dummy generator, and this dummy generator is going to be a signal to reserve and tell the reserve how much it needs to account for as a dynamic reserve. And here we set a dummy generator, and the main thing here is that the max capacity is larger than the combination of variable renewables in a given area. And a given area is whatever area you are talking about in terms of the reserve. For the UK or GB, it would be Great Britain and the accumulation of variable renewables in that area. The dummy generator needs a dummy region, but again, the main thing here is that the value of loss of load is set to 0. So we don't want any knock-on impacts from having that maybe 100, 1000. We just wanted to send that signal. The way the dummy generator is set up is very standard to any constraint. and we make it a hard constraint that, so basically we can see at the bottom that the dummy GB generator is negative, is -1, where the rest of them are 1, and we create it that way. And how we actually implement this in the reserve itself is, right now you can see we have highlighted that it's the Great Britain combo reserve that we talked about a little bit earlier. And here we see that the dummy generator is selected here as a generator contingency, and the risk factor then is 14.7, which is the equivalent to a percentage. We use 6.8% of generating variable renewable energy to set the dynamic reserve. Now, the next section, we're going to talk a little bit about the robustness of results. And what we're talking about here is, I suppose, going back to this scenario that we're talking about throughout, where we have high levels of variable renewable energy. When you have a lot of weather-dependent generation, means you have a lot of variability, and to account for that, you need to, I suppose, loads of sensitivities, and the robustness of results really needs to improve. And this is what we are trying to show you how we approach this. So we use a multi-sample approach for power generation representation, and we're I suppose, interannual wind and solar variations. So we're taking profiles for over 30 years, so we use 30 years, but you can use as many, if that's only dependent on the data you have. Here's two examples of publicly available data sources, which are fantastic sources to use if you want to even trial this approach. So one of our colleagues, Sean Collins, published a fantastic paper in the Joule journal in 2018, and where he's looking at the impacts of interannual wind and solar variations on the European power system. The scenarios he's using are from the European network of TSOs, and it's all about decarbonisation and different trajectories. And we'll talk through just a couple of his findings, which is graphically, it's very rich. So here we are looking at the wholesale pricing of the counterfactual. So along the horizontal, we have the penetration of variable renewable energy, and on the vertical, it's the wholesale pricing. So what we actually see here is a clustering effect of the 30 samples, and that is just down to the installed capacity, and then we just use the different profiles for the last 30 years. And you can see from a clustering, and from this you can get confidence that, because we can find out the mean, the standard deviation, the min, the max, all this data is there, and that's just one scenario. You can compare that then to a second, a third, a fourth, a fifth, and this is all fantastic stuff because it's very rich in detail. It gives you confidence. I suppose from, if I was an investor into a market, you look at this and you say, well, you have some idea of where wholesale prices are going to go as the penetration increases, all else being equal. And the thing here is that also that we're entering I suppose a new world where there's lots of variable renewable energy. Using single profiles, I'm not sure what Paul thinks, but using single profiles doesn't really cut it anymore. Like for robustness, you may need to add that extra level of detail.
Yeah, I'd agree, Fiac. I think, look, in the future, we're going to have more weather-driven variation with inherent variability. So I think the day of modeling one future scenario is gone, really. And, with tools like PLEXOS, really good, workstation independent samples. I think this work that Sean did here, he ran through about 150 different visions of the European power system over a weekend. I think that's really fundamentally rich in what that brings to you. And it doesn't take a lot of actual manual capacity to set up this model in the software. It's really computation time, and computation time is cheap.
We'll actually talk through how you set it up as well in 2 slides time. It's very straightforward. So moving on then, the next thing, this is also from Sean's paper where he looks at the CO2 intensity. So again, we're just going to touch on this for a moment, but you can see from the 5 scenarios that this clustering, I keep using that word, but it is kind of a clustering of results where you can get your mean, your standard deviation. You can it just provides confidence is the best word I can use in your results. So now we'll just talk about, oh no, sorry, one more slide. And this is based on results actually Paul and myself are currently working on. This is the same scenario as we talked about earlier. And here we have 30 individual samples that's, as columns. And what we're going to have a look at now is, so this is the level of variable generation of total energy system demand. And it's, we'll just say a little over 80%. When we add dispatchable power to this, it's about 90%, we'd say. But straight away, what you can see is from, you can see that there's an adequacy problem. So you can have just questions then, is the portfolio not adequate? Why is it not adequate? Is there not enough storage? And then we see, well, curtailment is actually low. So even if there was more storage, we wouldn't solve the problem. So there's a lot of questions can be answered, or a lot of questions can rise from this sort of analysis. From a regulator's point of view, an operator's point of view, investor's point of view, you can see maybe opportunities, and that's really what we are seeing with this sort of work. So next then, we'll just talk about how you actually set this up in your model, and it is very straightforward. So first of all, from the generator perspective, you set up the rating factor as it's equal to a variable. And you see here, this is the German onshore wind. So it's wind-DE is a variable. And then in the variable itself, you have the sampling method is user and a profile is a normal CSV. The CSV is set up as per normal. It's just with the columns 1 to 30 in this case. And then we go on to the stochastic settings. And this is really where you just need to know a little bit, and that the variable sample draw is set to 30, so you have 30 samples running. And the next thing then is that in PLEXOS we're using the independent samples in parallel, and that's a key part of what we're trying to do. From our experience, one of the things that we realized is around the reporting. And while this is not, this is just our experience sharing it, that what we found was when you model 30 times the amount, or you model using this sort of approach, you have 30 times the results. And what we found is that sometimes you don't always need all the period types. So what we did is we just deselected some of them. You don't have to do this, but it just helps with the solution size, and because sometimes that can be very, very large. So then afterwards, then it's just a case of associating the scenario and the specific simulation, and then you execute, and that's really it. And
that's really powerful. Like Fiac has displayed that, talked about that in terms of weather, but that could be anything. Those independent samples could be carbon prices, fuel prices, demand. You know, there's really a really big, rich landscape to explore there with the independent samples method. Yeah.
Do you want to make a point about data? About how to remember to slide?
Oh yeah, actually, what a nice feature in PLEXOS 8, actually the most recent version, which came out maybe a couple of weeks ago. I think the data handling abilities are absolutely phenomenal. We used to, maybe a lot of traditional users as well would hold a lot of, you know, you could have hundreds or thousands of individual CSV files linked to individual wind farms or power plants. But the new data handling capabilities in PLEXOS 8 allows you pretty much to store all those in one CSV file. Pretty much you know, whatever your computer can handle in terms of memory. And that's a real nice feature in terms of reducing the risk of human error, and also keeping your model nice and elegant and nice and clean. And it really reads in, it really gobbles up those data files really, really quickly and runs through the validation. So that's something we'd encourage users to check out as well.
And now we move on to the last section, which is high temporal resolution modeling. I suppose from my perspective, when I started modeling, we were always looking at hourly resolution models, and that's more reflective of market conditions and how a unit or units or a system is dispatched. But then I suppose the world we're going into with a lot of variable renewables, we kind of need to start looking at from an operational perspective and just a little bit more detail, and that's why we are looking at 5-minute resolution modeling. Here's a piece of work that I'm going to present just a few findings from Paul's piece of work that was published in 2014, where he compares different temporal resolutions. So if we look at a graph, on the horizontal, then we have, on the vertical, we have the average annual ramp intensity in megawatts per minute, and along the horizontal, then we have 4 different generation types. This is what I'm showing you here now is the ramp up intensity at 60-minute resolution, and then the ramp down intensity. So both of these are under 1 megawatt per minute. When we ramp this up and we look at higher resolution modeling, we see that the ramp intensity significantly increases, and same with the ramp down intensity. And so what this is doing is, when you model at 60 minutes, not all of the technical characteristics of a generator are binding. For example, some of your ramp rates probably won't bind if you have a CCGT, for example, whereas they might if you're looking at 5 minutes, or your main up times, your main down times. If you have an upward profile that you have to use, like a start profile, these sort of things are really captured when you look at 5-minute resolution. And I suppose from an operational perspective, or from an operational perspective, these technical insights are very powerful when you're talking about the ramp intensity, because if you have a power plant and you have to ramp around a lot, it's more wear and tear in the system, and more costs, more maintenance. The variable costs are going to be higher. But also, if you're making an investment decision and you're looking at battery storage, and you're looking at cycling, that sort of thing. It's just, there's a lot of rich data there by going by increasing your temporal resolution. The next thing now is we just kind of look at the system costs, and when you increase the resolution, what you get is this, I suppose, a capture of more of the system costs. For example, we have recently finished a paper that's in review, and the difference between 60-minute and 5-minute resolution is 4.5 billion euros. That's the equivalent of 3% of overall variable costs. And of that 3%, that 1% is associated with startup costs, and the other 2 is around fuel costs and carbon. Because at the end of the day, when you are ramping your plant around, you're less efficient, so there's more of a fuel burn or fuel offtake, and then this equates to more costs, and then there's like a lot of things that knock-on effects from here.
Yeah, and this is really important actually, as Fiac said. If you're trying to understand flexibility in the power system, it's also important that you capture inflexibility. So if you have some legacy steam plants, or if you have some quick start OCGTs, you capture their technical characteristics quite adequately. And as Fiac will show next, actually, 4.5 billion. That's quite a sum of money. Okay, it's small in percentage terms, and that's, I guess, one of the things. If you're interested in aggregate costs only at national level, you're probably not going to see a big difference in absolute changes between different scenarios. But if you're some person who's interested in storage, interested in flexibility, interested in those types of assets, well, then the 5-minute resolution modeling is something that you should really explore, and it's pretty easy to set up. Yeah, it is.
So the next thing here, we're just going to show you how easy it is to actually change the temporal resolution. Like, this is a short video, it's only 10 seconds long. So you get your horizon, you double click, and then there's a simple drop down menu, and you press OK. And that's really how complex it gets from the front end. But then there is limitations, but they're more machine based, which is different. So you might have to structure your model a little bit differently. We recently were working with Glenn Drayton on a paper, and he suggested that we nest one model into a different model in terms of just based on their temporal resolutions. So here we can interleave a 60-minute model and a 5-minute model, and this 5-minute is nested into the 60-minute. And what it actually does is the 60-minute model takes the unit commitment, or creates a unit commitment for all the big, large coal CCGT units, all these big units, and then passes that to the 5-minute simulation. So then the 5-minute simulation, all it has to do is decide what level of output it needs to be at, and not whether it's on or off. So that simplifies the problem a lot. What we also did was we shortened the horizon on the 5-minute simulation. And this, again, is just to reduce the problem size. And I'll show you how that was done next. So here we can see, this is in the hourly, the 60-minute resolution. We can see that it's hourly, and then it's the steps are of 1 day. When we look then change to the 5-minute resolution, we can see that the steps are now 6-hour steps with a longer look ahead. The look ahead is 18 hours. So because when you're interleaving models, each day is run in step. In this case, then you will have that 60-minute model, it would run for 1 day, and then the 5-minute model will have four simulations to equal that, and then we'll go to day 2. This, I suppose, this schematic has been around a while, so you might have seen this before. We just want to maybe just refresh your view of this, because really it's simple, but it's exactly what happens. So you have your day ahead model. In my case, it was a 60-minute model. It creates a solution, and that solution is passed into the 5-minute model. What you pass in, you can user define. It's really straightforward, and the help files are very good at showing you how to set that up. Then our 5 minutes, which here we call a real-time model, that 5-minute model creates a solution, and that is passed back into the 60-minute model at day 2. And then they're run in step the whole way through until the end of your horizon. And finally, this is our last slide. Here's just a short video on how you actually interleave models. It doesn't show you how you can decide exactly what you want to pass through, because you can send through exactly what you want, or it's more of a, it's just that it's more linked in terms of their end state. So here we can see it. So what we do is we can see that the horizon is, the empty or planning is 1 week, and we're running it for 3 days. So we execute this. This is just a day ahead on its own.